Okay, we're talking about the fundamental theorem of algebra, and with such an important sounding name, it is quite an important theorem. So the main theorem is sort of this thing here. Now, essentially what it's saying is about polynomials and their zeros. So suppose that we have a degree 7 polynomial. We expect 7 zeros. Now, for example, these zeros could be 3, they could be 2. You could have 1 plus I. If you have something like 1 plus I, you need to have its conjugate. That's very important. So the imaginary or complex ones, they will only ever come in pairs. One of your other zeros could be something like 3 take 4i. So again, you would need 3 plus 4i. And then what have we got? We've got 6 so far. And let's say that we have another zero, which is 2. So weirdly enough, you can actually have them be repeated. And if you're looking at a graph, generally, if it has an x-intercept, this looking like this would be a single. But if your graph instead looked like this, this would be a double. Now, I'd encourage you to maybe think about what a triple might look like. But zeros can be repeated. It's really important to mention that. So that's an example of a degree 7 and what zeros it could have. And there's a few corollaries here. So you can always factor any polynomial into complex linear factors. So you could always factor out this one. For example, it would start off like x take 3, x take 2, x take 1 plus I, etc., etc., etc. And if you want the polynomial to have real coefficients, so all real numbers, then these ones here will just make a quadratic, like you combine them together to make a quadratic one. All right, so that's pretty much what it says. The other thing to mention is because if a polynomial is odd, it's always going to have at least one real zero. I'd encourage you to think about maybe why that's true, particularly due to the fact that the imaginary ones always have to come in pairs. And there's also sum and product. So sum and product is a very useful sort of thing. If you do know what two of your zeros are, then you can pretty easily find what the full polynomial is just using sum and product. And I'll do a little example of that here. So we're trying to find a polynomial with the roots x equals 3 and x equals 4. The sum, so if you add them together, you get 7. And the product, so if you times them together, you'll get 12. Therefore, this polynomial, let's call f of x, is x squared take 7x plus 12. Done. Now, one thing that you do have to just put in is a scaling factor out the front. So a is in r. And that would just stretch the polynomial. It wouldn't change any of those x-intercepts. I do want to just verify that this is true for you. So verify here. If x equals 3 is a factor, then we're expecting x take 3 to be a factor and x take 4 to be a factor here. So you would expect f of x to look like that. So that would look like x squared take 4x take 3x plus 12 when you expand it out. Or in other words, a lots of x squared takes 7x plus 12, just like that. So, I mean, it does work. Sum and product just saves you a little bit of time. All right, now I've done sort of a partial proof of that just for x equals 3 and x equals 4. But what I'd really encourage you to do is try and prove that in general by starting off with x take p, x take q, and seeing if you can expand it out to get that formal statement of sum and product. Now the next example I'll show is just with the complex numbers. So this is a direct application of sum and product. We could do this the long way. So if it's got 3 plus 2i as a 0, we also know that 3 take 2i, the conjugate, is a 0. And this is by the fundamental theorem of algebra. So that's good. And if you wanted to do it the long way, you could expand it out as x take 3 plus 2i. And then the other factor would be x take 3 take 2i. And expand. We don't want to do that. That's going to take us way too long. And this is where sum and product comes in really handy. So the sum of these, if you add together the two roots, you're going to get 6, and then the imaginary bits will cancel out. And the product, so that's going to be 3 plus 2i with 3 take 2i. So you're going to get 9. Well, the middle terms will cancel out. This is actually a difference of 2 squareds. So you're going to get 2i squared. And I might actually write that as 3 squared there for completeness. But essentially this just becomes 9 take 4i squared, or 9 plus 4, which is 13. So therefore, f of x would have to equal a, lots of x squared, take 6x plus 13. Now be really careful. It's very easy to make a sign error here by forgetting that the sum always has a minus in front of it. So just keep that in mind as you're doing these questions. All right. One thing that we can actually do is we can check that we've got this right. So a could be any number. It doesn't actually matter what a is. If we go into equation solver on the calculator and we enter it as a degree 2, because that's what we've got, I'm going to enter the polynomial that I had, which was 1 lot of x squared, take 6 lots of x plus positive 13. If we solve that, we got no real roots. And that is because we haven't set up our calculator into imaginary mode. So you just go shift settings, a plus bi. Let's try that again. And we should solve it and get 3 plus 2i and 3 take 2i. So we've got it right. All right, suppose that minus 3 take I is a 0 of that horrible thing. We're going to find I. So this is an example of sort of what you end up being asked about this. So if this is a 0, by definition, it's like a x-intercept or a root. Now, we don't tend to use the word x-intercept with the complex ones because you don't actually see it going through the x-axis. But what this tells us is that p of minus 3 take I equals 0. Or in other words, 0 is a lots of minus 3 take I cubed plus 9 lots of minus 3 take I squared plus a lots of minus 3 take I take 30. Now, there's 2 approaches that you could take for this. You could do the whole Pascal's triangle binomial expansion for this. So you could do the whole a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. And you could expand out that first term like that. What's going to make your life a lot easier is just doing it on the calculator. But I would recommend practicing both just in case it comes up. So what I'm trying to do is minus 3 take. Your I button on the calculator is shift and then the 0. And then we're going to be cubing that. And you can see that that fully simplifies it, so it's a lot quicker. So a lots of minus 18 take 26i plus 9 lots of, and same thing here, minus 3 take I squared. We can work that out, so it's 8 plus 6i plus, and I might expand this out already, so take 3a, take ia, take 30. All right, so now I can keep expanding. So that gives us minus 18a. This is going to be minus 26ai. I might actually swap the order of those here because i's tend to come at the end. Then this one here, 9 and 8. It's a bit early in the morning for me to work that one out, but it's 72. 9 and 6, 54. All right, we can keep going here. What you really should be doing now is starting to collect real and imaginary terms. So real, that's real, that is real, and that is real. So we'll collect all those together. The 72 and the minus 30 will give us 42. And the minus 18 and the minus 3 will give us 21. So that's the real bit. That's good. And now I can start collecting our imaginary bits. So we've got that, that, and that. So we've got, with the a's, that's minus 27a. And we got 54 there, so 54 take 27a I. And this is just going to be a big plus in the middle. And that was our imaginary bit there. All right, so all this stuff should equal 0. And then we can solve the equation. So if we solve this one, we're going to get 42 take 21a equals 0. Because for this thing to be 0, the real bit has to be 0 and the imaginary bit has to be 0. So we get 21a is 42, or in other words, a is 2. If we solve this one here, 54 take 27a equals 0. So therefore 27a is 54. So a is 2. Thank goodness it is, because now we know that we definitely got it right. If you did get something different, then you're in trouble. The other thing that you could do, if you needed more sort of data to play with, is that we haven't mentioned it yet, but minus 3 plus I is also a 0 because that's a conjugate. So that's another tool in your toolkit if you need it. Although normally you don't, because if you had like two unknowns, A and B, for example, then you could figure out both A and B here because you'd have two equations, the real one and the imaginary one. All right, now that we know A, we can start dealing with this cubic. So we're just going to take a copy of that and we'll plug in the A value that we know, which was 2. So P of Z equals that. So that will be 2Z cubed and 2Z. And we want to fully factorize it. So as minus 3 take I is a 0, minus 3 plus I is a 0. Let's check that with the right ones. Yes, they were. By fundamental theorem of algebra. Therefore, and now if we look at the sum, so that's going to be minus 6, and the product is going to be minus 3 take I, minus 3 plus I. So that's going to give you minus 3 squared take I squared. So that's 10. So therefore, we have a factor of x squared plus 6x plus 10. You've got to be very careful about this sum flipping. It's very easy to make a sign error there. So this is a factor, and then we can put like sum and product there. All right, so we know that's a factor, and I've just realized that they should be z's rather than x's. The reason for z is z sort of implies they'll be imaginary solutions, whereas x implies that the solutions will be real. That's like a notation thing. Now, how do we get our other factor? Well, first thing that I want to do is just check one or two things to make sure we're on the right track. I will be going into equation mode. We're going to go polynomial, degree 2. 1, 6, 10 should give us these two imaginary solutions, which they do. And just so I definitely know that I got that A value right from before, I'm going to go back out of here, go up to a degree 3, and enter the full polynomial. So that is 2, 9, 2, and minus 30. I'm hoping to see those two imaginary solutions I found before, and we can see that another solution is 1.5. So we're expecting to get another real one. How do we get it? Well, the answer is polynomial division. So we can do a division. It's going to be z squared plus 6z plus 10 there. And then it's going to be 2z cubed plus 9z squared plus 2z take 30. Now again, since we've seen a few divisions at this point, I would encourage you to pause the video and try this one just to practice your division skills. If not, I'll go through it. And this one is a little bit different because we've got a quadratic here. How many times does z squared go into 2z cubed? It goes in 2z times. We now need to times 2z by all three of those pieces. So it's going to be 2z cubed plus 12z plus 20. Subtract. 9 take 12 is minus 3. 2 take, let's see, that should have a z on the end. 2z take 20z is minus 18. And we can pull down the minus 30. All right, how many times, oh, that should be a z squared as well. How many times does z squared go into minus 3z squared? It goes in minus 3 times. Now let's check. So minus 3 now needs to come in and times by everything. So I get minus 3z squared. Take 18z when I do it with the 6, and I get take 30 when I do it with the 10. And thank goodness we get a remainder of 0, because that's what we were hoping to get, given that this was a factor. It's really important that that was 0, otherwise we've done something wrong. So, using this, so therefore we can write f of x as, now I don't think, let's see, the number in front of the z cubed there was 2. So we just have to be very careful about this. But given the way we've sort of divided this out, the 2 gets captured in that 2z take 3 term. So z squared plus 6z plus 10. And then the other factor was 2z take 3. So it's a good idea to always consider that you might have an a value out the front. But if you imagine expanding this out normally, the first term is going to be 2z cubed. And that does match that one. So, yes, a was just 1. So we don't even need to worry about an a term there. And I believe this thing was called p of z. All right, cool. So there's our polynomial. This one we already saw had our zeros of -3 plus I and -3 take I. And if we try and solve this one to get our zeros, we get 3 halves. The reason you do is because you're trying to solve 2z take 3 equals 0. You rearrange that equation, you're going to get z is 3 halves. And we're done. Now, I will just quickly point out that that is what we got on the calculator as well. So that is good news and good to check that.